Bismillahirrahmanirrahim. In this lecture, we are going to speak about the gradient and directional derivative of scalar field. Scalar field means we are speaking about a scalar function, not a vector function. And in this part, we are going to speak about the gradient first, then we speak about the directional derivative, and also we will discuss the maximum value and minimum value of the directional derivative. So starting with the gradient of a function. The gradient of a function is given by nabla of f of x, y. Let's speak about the two variable function or two-dimensional vector or function or three-dimensional function, f of x, y or f of x, y and z. The gradient is just the partial derivative, the sum of the partial derivative multiplied by you can say, put it in a vector form. So the gradient of a function f of x, y equal to the partial derivative f with respect to x, I, plus partial derivative of the function with respect to y, j. If we have x, y, z, then we will add the third component, which is the partial derivative with respect to z multiplied by k. Or we can say just simply it is f of x, I, and the notation of the partial derivative plus f sub y, j. So this is the gradient of a scalar function. So the gradient of a scalar function is a vector. You have to notice this point. We have a scalar function, and the gradient of the scalar function is a vector. For example, let's take compute the gradient. Of the following. 1. With that f of x, y equal to 5y minus x to the power 3y squared. Let's find the gradient of this function. So the gradient given by nabla f of xy equal, this is nabla, equal to f of xi plus f of, or f sub x, not f of x, f or the partial derivative with respect to x and the partial derivative with respect to y. If we find the partial derivative with respect to x, we consider y as constant. If we differentiate the function with respect to x, we will consider the y variable as constant. So the derivative of 5y with respect to x equal to 0. So the partial derivative with respect to x is equal to minus 3x square y square. This is the constant. This is the first derivative. F sub x given by minus 3, okay, write it there. F sub x equal to minus 3x square y square. The first one is 0, because there is no x, so it is constant with respect to x. F sub y is equal to, the first term will give me 5, second one is 2x to the power 3y. So the gradient now is minus 3x square y square I, this is the first component, plus f sub y, or f sub y is given by 5 minus 2x square, y square multiplied by k. So this is the gradient of the given function fy or 5y minus x to power 3y to power 2. The gradient is minus 3x square y square I plus 5 minus 2x square y square j. Another one, number 2. Let f of x, y, z equal to xy square over z. Or this can be written as x y square z to power minus 1. And I need to find the gradient of this function. So the gradient of f of x, y, z equal to f sub x, or the partial derivative with respect to x I plus partial derivative with respect to y j plus the partial derivative with respect to z k. This will give me differentiate with respect to x, it will be y square z to power minus 1 I. This is the first component. Second one, plus with respect to y, it will be 2 x y z to power minus 1 j. With respect to z, it will be minus 1 x y square z to power minus 2k. So this is the gradient of the given function f of x, y, z. The gradient will be a vector function given by y square z to power minus 2i plus 2xy z to power minus 1j minus x y square z to power minus 2k. One more example. Number 3. F of x equal to len x square plus y square plus z square. So the gradient in this case it is f of x or f sub x I plus f sub y j plus f sub z k, the partial derivatives, which is equal to, with respect to x, or the derivative of len f of x, the derivative for this one is equal to f prime divided by f. So it will be the partial derivative with respect to x. The function is written down in the denominator as x square plus y square plus z square. And with respect to x, it will be 2x I plus for y, it will be x square down plus y square plus z square to y. For z, this will be j plus x square plus y square plus z square and 2z up multiplied by k. So this will be the gradient of the given function. Sometimes we need to find the gradient at a specific point. For example, let's find the gradient or commute. Let's say not find. the given function main point. Given that f of x y equal to x squared minus 4y squared, and we need to be at the point 2 and 4. This means that all what we need just to find the gradient and then substitute x and y by 2 and 4. So the gradient of this one, gradient of f at 2 and 4 is equal to, you can write it as in the other form, it is f sub x, f sub y at the given point 2 and 4. This is the other notation of the vector. The partial derivative with respect to x is 2x. Partial derivative with respect to y is minus 8y at 2 and 4. Now substitute, replace x by 2 and y by 4. This will be 2 times 2 is equal to 4, and minus 8 multiplied by 4 is minus 32. So the gradient at 2 and 4 equal to 4 and minus 32. So this is the idea of finding the gradient of a scalar function. Partial derivative of x multiplied by I plus partial derivative of y multiplied by j. The other point in this vector now will be the directional derivative. The directional derivative is defined as, okay, let's say this, start with the definition now. The directional derivative of a given function of function z equal to f of x, y in the direction of a unit vector. U equal to sine theta I plus sine theta j. Is given by d u. This notation to mean the directional derivative in direction of the vector u, or the unit vector u f or cosine I plus sine theta j. We know that the meaning of the derivative is change, is rate of change. So when we say that directional derivative means we are looking for change of rate in some direction. We will be given direction in which that we need to check the change of rate of the scalar function, like moving particle or whatever is the function there. It has some change of rate in different directions. When we change the direction, the change of rate will be changed also. So at a specific direction, we need to find the change of rate, and that's what we mean by directional derivative. So it's given by f of x plus h multiplied by cosine theta y plus h sine theta. Minus f of x y divided by h, where h goes to 0. So this is the direction derivative given by this formula. But provided that the limit exists. Other notation for this one, it can be written as d u of the function f of x, y equal to the gradient of the function f of x, y dot product with the unit vector. This is the other notation for the directional derivative. To compute the directional derivative, we need to find the gradient and then we multiply or dot product with the unit vector. For example, let's find the directional derivative of f of x, y is equal to 2x squared y to the power 3 plus 6x y at 1, 1 in the direction of a unit vector whose angle with the positive x-axis is y over 6. So we need to find the directional derivative of the given function f of xy, which is equal to 2x squared y to the power 3 plus 6xy at some given point, which is 1, 1 in this case, in the direction of a unit vector whose angle with the positive x-axis is y over 6. So what we need to find now, I need to find the gradient first. The gradient is f sub x, f sub y. The partial derivatives, which is equal to f sub x is equal to 4x y to the power 3 plus 6y. This is the partial derivative with respect to x. Now we differentiate with respect to y. It will be 6x squared y squared plus 6x. So this is the gradient. Now we can find the gradient now, or evaluate the gradient at the given point, 1 and 1. So the gradient of the given function at 1, 1 is equal to, replace x by 1 and y by 1, it will be 4 plus 6 equal to 10, and 6 plus 6 equal to 12. This is x equal to 1 and y equal to 1. Let x equal to 1 and y equal to 1, and then compute or find the values. It will be 10 and 12. Now the unit vector at pi over 6. Unit vector at theta equal to pi over 6. The unit vector equal to cosine pi over 6 and sine pi over 6, which is equal to cosine pi over 6 will be third root divided by 2, and sine is 1/2. Now I have the gradient, I have the unit vector at the given direction, which is theta equal to pi over 6. We can find the directional derivative. Then the u of the function, direction derivative in this direction, x, y equal to the gradient at u. Gradient is given by 10, 12. Dot product with square root of 3 divided by 2 and 1/2 is equal to 5 square root of 3 plus 6. So the direction derivative is given by 5 square root of 3 plus 6. And you can notice one thing there. The direction derivative is a scalar function. Directional derivative is a scalar function, it is not a vector. We have a gradient dot unit vector. It is a vector dot another vector. And the dot product of two vectors will give me scalar value or a scalar function. So this is the directional derivative of the given function at the given point 1 and 1. Changing the point will give me different value for the directional derivative. Or also changing the angle with the positive x-axis will give me different value of the directional derivative. Changing the direction will give me different values.